So now let's focus on a very popular model called the Cournot model. And also, I assume that most of you have seen this model before. It's a model from game theory because we have strategic interaction between two firms, three or four firms, and nevertheless, this model is also usually part of, for example, microeconomic courses and other different courses. So in order to see this model, you don't necessarily have to take a particular game theory course. But so in this example, we have two firms. So the players are these two firms. And then these two firms sell identical products. So consumers actually don't care if they buy the unit which was produced by firm 1 or if they buy a unit which was produced by firm 2. So they just want, they choose whatever. So they see no difference between the products produced by the two firms. So the two firms have to choose quantities. Two firms produce identical products and choose quantities. Two firms produce identical products and each firm chooses its quantity. So player 1, firm 1 chooses Q1. So player 1 chooses Q1, player 2 chooses Q2. And then, for example, player 1 says, I would like to produce 5. Player 2 says, I would like to produce 6. So where does the strategic interaction come into play? Well, the strategic interaction comes into play when we look at the market, because we say that the total quantity is equal to Q1 plus Q2. So this is the total quantity which is produced by the two firms. And then we have the common demand function, which says P is equal to A minus Q. And this is exactly where strategic interaction comes into play, because if I produce 1 unit extra, this means that I decrease the price both for myself and then also for the other firm. Also, I produce, for example, 5 units, but then which price will I get for those 5 units? Well, actually, it depends on the quantity that the other firm has chosen. So let's plot it right here. So this is our demand function. So where we have Q, the total quantity, and then we have P. And we have here A, and then we have this demand function. So we can write that P is equal to A minus Q. So we go, every time we go 1 to the side, then we go 1 down, which means that we actually also have A over here. The final detail about this model is that both firms have, of course, some costs. What are the costs of producing 1 unit? And then we say that the cost of producing 1 unit is C. Okay, so no matter how many units you have already produced, it always costs C dollars to produce, or C euros, or C Danish krona to produce one extra unit. So the marginal cost is always equal to C. So if you want to calculate the total cost, then we just say C multiplied by the total number of units that particular firm has produced. So let's see if can we say that this is a game from game theory? Yes, we can, because we have defined the players. The players are from firm 1 and firm 2. Maybe let's do that more formally. So we have players. We have firm 1 and firm 2. Then we have the strategy spaces. Strategy spaces. So which actions can they take? And then we have S1 is equal to S2, and it's equal to 0, infinity. As you can see, this game is a bit unusual because the strategy spaces of both players actually include an infinite number of elements. So in all the examples we have seen before, every player had, for example, two possible strategies, or three possible strategies, for example, to betray or stay silent. And here we have actually an infinite number of elements. So those are the strategy spaces. So player 1 chooses Q1, player 2 chooses Q2. So every player needs to choose a quantity. And then the payoffs, we need to define the payoffs. And here we have, for example, for player I, we have Pi, which is a function of Q, for example, Qi and then Qj. So my own payoff and then the other player's payoff. So we have the price, which we get A minus Q. That's the price, multiplied by the number of units that I produce, Qi. So this is my total revenue. And then now I need to subtract the total cost. And my total cost is C per unit multiplied by Qi. So this is basically equal to the price. This one is total revenue, and this is total cost. Okay, so we have total revenue minus total cost. And the question is, what is the unique Nash equilibrium in this game? And let's try to solve this question. So in order to find the Nash equilibrium, each player needs to maximize its payoff given the choice of the other player. So let's try to maximize the payoff of player 1, for example. So we have player 1's is equal to payoff, profit is equal to A minus Q multiplied by Q1 minus C Q1. Again, total revenue minus total cost. This is equal to A minus Q1 minus Q2 multiplied by Q1 minus C Q1. And then let's just also multiply, say, A Q1 minus Q1 squared minus Q1 Q2 minus C Q1. And then what we want to do now is we want to differentiate this profit function with respect to Q1. So if I'm player 1, then for me Q2 is a constant. So I cannot choose Q2. Q2 is something that the other firm chooses. On the other hand, I can choose Q1. So, and I need to choose that value of Q1 which maximizes my profit. And in order to do that, I need to differentiate the profit function and then differentiate it with respect to Q1. So what do we get? We get A minus 2Q1 minus Q2 minus C is equal to 0. And let's assume that this is, we can check, but let's skip the step. We can check that this is actually the maximum and not the minimum. But let's skip the step in this case. So we have A minus 2Q1 minus Q2 minus C is equal to 0. And from here we want to isolate Q1. So we have 2Q1 is equal to A minus Q2 minus C. And then we have that Q1 is equal to A minus C divided by 2 minus 1/2 Q2. And this is what we have for player 1. So, and this is actually reaction function of player 1. So this is reaction function of player 1 as a function of Q2. Meaning that this function shows us how player 1 should react in order to maximize its payoff. So suppose player 2 says, I have produced 10, so Q2 is equal to 10. How much should player 1 produce in order to maximize payoff? Then what I do is I simply put 10 in here, say Q2 is equal to 10, and then I simply see what the value of Q1 should be. And then instead player 2 says, well, I have produced 20. Then again, I say Q2 is equal to 20, and then I see what is the optimal value of Q1. So basically this equation, this reaction function shows how player 1 should react when player 2's quantity is revealed. Yeah. So similarly, because we have symmetry in this game, so we can write by symmetry. We have that Q2 is equal to A minus C over 2 minus 1 over 2 Q1. Okay, and this is the reaction function of player 2. So this, it says, if player 1 has produced a certain quantity, how should player 2 react? And so let's plot those two reaction functions. So we have, for example, here we have, we have Q1, and then we have Q2. So what is the reaction function of player 2? Let's plot it first. A minus C half, so it looks like this, A minus C over 2, and then it goes like this. So every time we go 1 to the side, we go 1/2 down, meaning that here we will have A minus C. So similarly, we can plot for player. Similarly, we can plot for the other player. So maybe first of all we can write this is a reaction function of player 2 of Q1. Now let's choose a different color. For example, let's choose the red color. And if we want to plot the other one, so this one Q1 is equal to A minus C divided by 2 minus 1/2 Q2, then it would actually look like this. Again, A minus C over 2, and here we will have A minus C. And now let's find where do we have the Nash equilibrium. So suppose that we are here. Is that a Nash equilibrium? So this is the quantity that player 1 produces, this is the quantity that player 2 produces. The question is this a Nash equilibrium? And of course the answer is no. So this is A1 as Q2. Of course the answer is no. Because if player 1 produces this quantity, what is the optimal quantity that of player 2? Well, that would be an optimal quantity of player 2. So player 2 would say, no, I would like to deviate. Instead of producing this quantity, I should have produced this quantity. So I would like to deviate and actually increase my quantity. So player 2 wants to deviate it. Similarly, player 1 wants to deviate, because we can see that if player 2 produces this quantity, then what is the optimal quantity of player 1? The optimal quantity of player 1 would actually be this one. So also player 1 says, okay, given that player 2 produces this quantity, I should not have produced this quantity, but I should instead have increased it and produced this quantity. So basically both players would like to deviate, and of course when both players would like to deviate, we do not have a Nash equilibrium. So at any point outside, we will have that both players would like to deviate. Now suppose that we take a point on the line, on one of the lines. For example, let's suppose that we take this point. The question is this a Nash equilibrium? And again, the answer will be no, because let's first ask player 1. Given that player 2 produces this quantity, are you producing the correct quantity or do you want to deviate? Player 1 says, yes, I'm producing the correct quantity, I do not want to deviate. So player 1 is actually happy. Player 1 is producing the correct or the optimal quantity, given that player 2 produces this quantity. On the other hand, when we ask player 2, do you produce the right quantity when player 1 produces this quantity? So this is the quantity that player 1 produces, and then we ask player 2, is this the correct quantity that you are producing? And then player 2 actually says no, because according to my reaction function, I should have produced this quantity. So basically I would like to decrease my quantity from Q2 star to, for example, Q2 hat. So player 2 wants to deviate. So similarly, if we take any point on the line, either on this line, on the red line, then player 2 would like to deviate. If we take any point, or let me put it in another way. So if we take any point on this red line, then player 1 does not want to deviate, but maybe player 2 would want to deviate. If we take any point on the black line, so player 2's reaction function, then again one player doesn't want to deviate while the other player wants to deviate. And there is only one place in this whole chart where both players are not interested in deviating, and that place is actually that spot is actually where those two reaction functions cross here. So over here, player 1 doesn't want to deviate, and then player 2 does not want to deviate either, because given that player 1 produces this quantity, it's optimal for player 2 to produce this quantity, and given that player 2 produces this quantity, it's optimal for player 1 to produce this quantity. I'm sorry that the chart is not symmetric. Of course it's symmetric. So in the Nash equilibrium, they produce exactly the same quantities. So that's like the general idea. So we want to find the quantities which ensure that we are in the Nash equilibrium. So that's the question. What are the quantities in this Nash equilibrium? So let's try to find the quantities in the unique Nash equilibrium that we have in this game. So in order to find the Nash equilibrium, we need to find the point where these both reaction functions cross. So we need to find the point which are marked with green. In order to do that, we have to see where the first reaction function, so this one, where it crosses with this one. So we have actually two equations with two unknowns, Q1 and then Q2. So what we can do is we can just take, for example, Q2 from the second equation and then substitute it into equation 1, and then we will get the solution. So two equations and then two unknowns. On the other hand, we can actually make things a little bit easier for us, because we can see that the game is symmetric, meaning that in the solution both players will have exactly the same quantities, and it will actually make things for us a little bit easier. So we can, for example, write Q1 is equal to Q2. We know that this will be true in the equilibrium because both players will choose exactly the same quantities. And then we can, for example, say that take one of the reaction functions, say Q1 is equal to A minus C divided by 2 minus 1 half Q2. And then because we know that Q1 is equal to Q2, then we have A minus C divided by 2 minus 1 half Q1. And so from here we have that 1 and half Q1 is equal to A minus C over 2, and then we can, for example, say that 3Q1 is equal to A minus C, and then we have that Q1 is equal to A minus C divided by 3, and this is actually the solution. So by symmetry we have that Q2 is equal to A minus C divided by 3. So this is basically the quantities in our Nash equilibrium, meaning that this quantity here is A minus C divided by 3. Let me use a new color. This one, and then this one, A minus C divided by 3, and then we also have here A minus C divided by 3. So we can write that our Nash equilibrium in this game is Q1, Q2, and it's equal to A minus C divided by 3, A minus C divided by 3. So here we have found the unique Nash equilibrium in which no player wants to deviate. Then let's calculate what is the price in the equilibrium. So what price will consumers pay? So we have P is equal to A minus Q1 minus Q2, and that's equal to A minus C over 3 minus A minus C over 3, and this is actually A plus 2C divided by 3. This is something that you can check. So this will be the price that consumers will pay in the Nash equilibrium. There is one more thing that I would like to mention about the Cournot model. In this model we have a bit interesting setup. In this setup both firms choose their quantities, then they bring those quantities to the market, and the market tells them, for example, the price is 5. Usually if I had a firm, I would expect to go the other way around. So I would for example say, okay, these are the goods that I'm producing. If I set the price to 10, how much will I be able to sell? So I go to the market and ask the market, if I set the price to 10, how much will I be able to sell? If I set the price to 11, how much will I be able to sell? If I set the price to 8, how much I will be able to sell? So this would be the usual setup, but in this case, in the Cournot model, we go the other way around. We first produce a certain quantity. For example, we say we produce 1,000 units, and then we go to the market, and then we ask the market which price will I be able to get for those 1,000 units. And the question is, where does such setup exists, where you first choose the quantity and then the market tells you the price? And actually one of the examples is, for example, oil. So when you decide how much oil you should bring to the market, then you should decide on the quantity. So you look at the market, and then you say, okay, I will bring this quantity to the market. And then you understand that if you take more oil out of the ground and then bring more oil to the market, then you basically decrease the price both for yourself and then for the remaining players. Another example would be fisheries. In fact, we have a paper in which we used a simple Cournot model with 3 firms. or with three players, and the three players were European Union, Norway, and Iceland. And then we tried to model the situation that occurs in the Atlantic Ocean when fishing mackerel today. And actually, the simple Cournot model describes the situation very well. So fisheries would be another example. So you have different ships from different countries. Each ship decides how much mackerel should be brought to the market. And again, the market tells you what price you will be able to get for the quantities that you decided to produce.